Okay, let's talk 7.2 U-Substitution. In your packets, if you have this packet, there's more information than what's given here. I'm just going to go straight into the U-Substitution. This video is going to be a little bit longer, and I'm on a little bit of a tight schedule here. So I'm going straight into the examples. They're going to start out giving us U values that we're to substitute, things that we want to get from there. Once we determine what we're going to use for U, we want to know what du is. Now, that would be the derivative of this. And how do we get there? We really take the derivative with respect to x on both sides. So it's really du dx. The derivative of u with respect to x is just du dx equals derivative of 3. That is 3. So what is du? Multiply both sides by dx. Du is 3 dx. Okay. So after I get that, if this is a constant and there's not a variable in here, I like to divide that constant back away, so dx could be replaced by 1/3 du. That's a step that, like on Slater and some videos, some people don't do this. I really like that step. I think it makes it really clear. You don't have to do it, but I highly recommend. So what do we get here? I get integral sine of u. In place of dx, I can put 1/3 du times 1/3 du. Now, we might get to the point where we just immediately put that 1/3 out in front, because of 1/3, a coefficient, something multiplied by everything inside, a factor, it's a constant, can be pulled out. So I get 1/3. The integral of sine is negative cosine. Take a look. If I take the derivative of cosine, I get negative sine, so I need the opposite of that. And then we go plus the constant. So I end up with negative 1/3 cosine of what was u? U was 3x plus c. Now, I believe we could do that problem without, even though there's a little chain rule component to it, I believe we could do that problem without U-substitution. But we're not going to be able to do all of these that way, so we're going to practice this. One of the challenges is going to be pretty soon they're going to not tell us what u is. But for right now, u is 2x. Therefore, du is 2 dx. Or maybe more importantly, dx is 1/2 du. Okay, so what do we have? We have integral secant u, tangent u, and now, what else? That takes care of these guys. What's left? dx. I wish I could replace it. I can. Times 1/2 du. 1/2 out in front. It's a factor, constant factor. The derivative of what gets us to secant u, tangent u? That is secant u. But u is 2x plus c. Why plus c? Well, because if I take the derivative of this, I get back to here, the derivative of c becomes 0. See, we could have any number on there we want. I'm going to hold off on problem c just for a moment because it's kind of weird. We'll come back to that. It's a little bit different. This one, what a mess. Without U-substitution, I wouldn't have an idea what to do. U, we're going to let U be this guy. We're going to try this. Now, why do they choose that? Well, there's some wisdom there. Maybe we could have chosen U to be this thing. But I think you'll see where we're going with this. So du is derivative of 1, 0, derivative of negative cosine. Derivative of plain old cosine is negative, so this would be positive sine of t on 2 times the inside derivative, 1/2 dt. It's really du dt, du on dt, but we have to multiply that across. Okay, let's take a look at our derivative a little bit. What do I like about the derivative? I like that the derivative is sine of t on 2. I like that there's a dt. I'm not crazy about this 1/2 in there. I'm going to go 2 du equals sine of t on 2 dt, and take a look, that's that whole component right there. So my integral with substitution becomes, this is u squared times 2 du. 2 du gets to take the place of all of that, times 2 du. So once again, I get 2. out in front, it's a constant, it's a factor. What's the derivative of u, or the antiderivative of u squared? That is u to the third on 3 plus c, or 2 times, what is u? U is this mess. I'm going to go 2/3 times u cubed. What is u? This mess, 1 minus cosine t on 2 to the third plus c. Okay, now let's talk about this problem C that's really kind of a mess. I mean, I think you're going to see that our original thinking might not even be for u to be x on 3. If I look at this problem, there's at least some reason why I'm choosing u to be that. There's at least some reason why I'm choosing u to be 2x. I can see why we might choose u to be 3x here. I'm not certain why we would choose u to be x on 3. Now, if u is x on 3, I could say that x is 3u. I'm going to leave that hanging there for a minute. You'll see where I'm going with this shortly. Okay, so du, derivative of this, is 1/3. Multiply the dx over, and we get that. So I could also write dx could be replaced by 3 du. One thing I'm not crazy about, I don't really like the dx in the numerator as a factor. I just like it at the end. You don't have to do this, but I'm going to treat this as 1 on x squared plus 9 dx. I suspect a lot of you will adopt it just because your teacher does it. It's my idiosyncrasy. Sorry. All right, so with that, this is kind of weird because it's like I'm not looking to put u in place of x on 3. I don't even have an x on 3 here. So in place of x, though, I could put 3u. So I get integral 1 on 3u squared plus 9 du. Well, this dx can be replaced by 3 du's. So I'm going to put the 3 out in front. I'm going to clean this up a little bit. 1 on 9u squared plus 9 du. Take a look at that for a second and see if that speaks to you. I don't think this is a coincidence that we got this 9 and 9 here. In fact, I can factor out of this fraction 1/9. And if I put a 1/9 out in front and made this u squared plus 1, I could pull that 1/9 out and join the 3. So I get 3 times 1/9 times the integral of 1 on u squared plus 1 du, and now that thing is speaking to me. This is the antiderivative of this guy is tangent inverse u. So what do I get? 3/9, 1/3, tangent inverse of u. What is u? X on 3 plus c. And that's it. So I really believe our thought on this might not be choose a value of u. It's like, what do we want x to be? I want x to be 3u, because then I can match that 9. So that one's kind of quirky, stands by itself, but you'll see 1 or 2 more of those, and hopefully that will become something we recognize right away. Okay, let's move on here. We got a bunch of these to get through. U-substitution. They're not giving us anything to go with here. So I could say, let's let u be 1 minus x all squared, or I could say, let's let u be 1 minus x, or maybe even I could say let's be negative x. So I'm going to give some thought to this. I don't want to just randomly pick things, although I'm going to do a problem in a little bit where I'd show you that we might have some challenges along the way. If I was to have u be, let's say, 1 minus x, the derivative of that would be negative 1, and I can handle a negative 1. What I can't handle is if I let u be 1 minus x squared. What's the derivative of 1 minus x squared? In the derivative of 1 minus x squared, the 1 minus x is going to survive. It's going to be 2 times 1 minus x to the first times the inside derivative of negative 1. And when that x survives, if it's not accounted for in here, we got problems. I'm going to let u be 1 minus x. You'll catch on. Then du is negative 1 dx, or maybe better yet, dx is multiplied by negative 1 both sides, negative 1 du. It's got a little crowded here. Again, I'd rather this be integral 1 on 1 minus x squared, need a parenthesis around there, dx. Sorry, got a little bit messy, getting a little bit tight here. So if u is 1 minus x, then my integral becomes 1 on u squared. Dx can be replaced with negative 1 du. I get, clean this up a little bit, negative out in front, negative 1, times, I'm going to make this u to the negative second du, and that gets me negative 1 times, this would be u to the negative first on the negative 1 plus c, or negatives cancel, u to the negative first, 1 on u, so final answer, here we go, got crowded, 1 on u is 1 minus x, negatives cancel, 1 on u plus c. Okay? Well, that's it. I think maybe we could have done that one without u substitution. I'm not sure on this one, though. So our choices for u. I want to do some planning here. I can choose tangent to be u. I can choose square root of tangent to be u. I could choose secant to be u. I could choose secant squared to be u. I could try to do some trigonometric transformations and change secant squared into perhaps tangent squared plus 1. Maybe that would be a good idea. So what I'm going to do is I'm going to just think ahead like I was playing chess. Let's say I chose secant or tangent to be u. What's the derivative of tangent secant squared? I love it. It's worth giving that a shot. If I chose u to be secant, what's the derivative, or what's the derivative of secant? Secant gets me secant tangent, which is sort of good, but I don't want plain old tangent. I want square root of tangent. So I'm going to give this a try, and I'm going to write. Normally I'd be writing softly in pencil here because I might be going back. So I'm going to have u be tangent of x. Then du is secant squared x dx. Look at this. Du is all of that. That's wonderful. I can replace du with that. And then I can get square root of tangent, or u square root, or u to the 1/2, just du. Du takes care of this. U to the 1/2 takes care of that. The integral of u to the 1/2 is u to the increase the exponent by 1. Put it over that same increase by 1. Put it over 3/2, but that's times 2/3. So I get 2/3. What is u? U is tangent of x to the 3/2 plus c. How about that? Okay, here. This is a problem that on first inspection begs for us to say u is 4x plus 2. Let's go with that. If that is the case, then du is 4 dx, or I'm going to write it over here, dx is 1/4 du, and I get, setting this up, integral is tangent of u, dx can be replaced with 1/4 du. I can put the 1/4 out in front. So the derivative of what gets me to plain old tangent? It's not secant squared. See, the derivative from tangent gets us to secant squared. The derivative of what gets us to tangent would be tangent's antiderivative. I don't know. We don't have a rule to get us straight to tangent. So I've got to punt here. What are my other choices for u? Maybe none, unless I can either algebraically or trigonometrically manipulate this. Let's think identities for tangent. Tangent can be 1 on cotangent, but I don't have an antiderivative that gets me, or I don't know the antiderivative of cotangent. How about if this was tangent squared, then I could say secant squared minus 1, but it's not, and I think there'd be a lot of work with a radical involved in solving that, solving tangent squared for just tangent then. What other option do we have? How about integral sine of 4x plus 2? Seems like this is going to be a lot worse. Cosine of 4x plus 2 dx. Now my choices. Maybe u could be 4x plus 2. I get sine of u on cosine of u. Maybe u could be sine of this, sine of 4x plus 2. Maybe u could be cosine. Listen to this really, really closely. If I choose u to be sine of 4x plus 2, the derivative would be cosine of 4x plus 2, that's good, times the inside derivative 4, that's manageable, times dx, but dx would be in the denominator of that. I'd need dx to be in the denominator there. If I choose u to be cosine of 4x plus 2, what's du? du is negative sine of 4x plus 2 times 4 dx. And I'm invading space on poor little problem D over there. Take a look at that. I love this. I love that dx not being in the denominator. I just don't care so much for the negative 4. So I'm going to rewrite this. du is, so therefore I can go, let's multiply both sides by negative 1/4, and I get du takes the place of sine of 4x plus 2 dx. This takes the place of that guy. So what do I end up with? If u is cosine, this is 1 on u times negative 1/4 du. So I get negative 1/4. Pull that out in front. Antiderivative of 1 on u, that is ln of u is cosine of 4x plus 2. I'm going to leave this just for a second. I'm going to come back to that. Plus c. Now, you need to be alert to something here. We just introduced ln in this problem. Here's something to take a look at. If you look at this integral right here, there's nothing wrong right here with u being a negative, but we got problems with once I go to ln u if u is a negative, because there is no, e cannot be raised to a power and become a negative value. That's what that's saying. We can't put negatives into ln's. We can't have negatives. That's therefore the absolute value. So is it possible in the initial problem that 4x plus 2 is negative? Sure. 4x plus 2 could be negative here. Therefore, we can't allow this guy. Now, 4x plus 2 can be negative here, but what we can't allow is for cosine of 4x plus 2 to be negative. So when you check back in the book answers, you're going to see we have an absolute value situation here, because cosine can possibly be negative. We can't let that happen. Okay, I don't have a whole lot of room for this, but I don't need it. If I choose u to be 3z plus 4, then I'm going to end up with cosine of u. And cosine, I got an antiderivative for cosine. It is sine. So yes, u equals 3z plus 4. du equals 3 dz. Maybe better, dz equals 1/3 du. So what do I end up with here? Integral cosine u, in place, that takes this. In place of dz, I can put 1/3 du. So 1/3 out in front. Antiderivative of cosine is sine. Sine of u, because derivative of sine is plain old cosine. What is u? 3z plus 4 plus c. A constant. Okay, number 6. My thoughts. U could be x. Well, that would be silly because it doesn't get me very far. U could be 1 on x. What's the antiderivative of 1 on x? Might say ln. Careful with that. Or u could be ln x. This is the same as ln x to the 6th, by the way. What's the derivative of ln x? Oh, that's 1 on x. Okay, derivative of ln x, antiderivative of 1 on x gets me back to ln. But how about this? How about we go u is ln x, then du is 1 on x dx. 1 on x dx takes care of all of that for me. Oh, that's great. So what do I have? I have u to the 6th, and dx gives me the 1 on x dx, or the dx on x. So we got it. So I end up with u to the 7th on 7 plus c, or ln x to the 7th on 7 plus c. Well, that's all right. Okay, choices, choices. U could be s to the 1/3. U could be s to the 4/3 minus 8. U could be cosine of s to the 4/3 minus 8. The problem is if u is cosine of, du is going to have a sign. I have nothing to account for the sign. If u is s to the 1/3, the derivative of u is s to the negative 2/3. Not crazy about that. If u is s to the 4/3 minus 8, the derivative of that is 4/3 s to the 1/3. Love the s to the 1/3 ds. What I don't like is the 4/3. S to the 1/3 ds is great. I'm going to multiply both sides by 3/4. So s to the 1/3 ds can be replaced by 3/4 du. I get integral cosine of u times 3/4 du, or 3/4. Bring it out in front. Integral of cosine. Cosine's antiderivative is plain old sine, sine of u, but u is s to the 4/3 minus 8 plus c. No way is it that easy. All right, U-substitution. Here we go. This one, I wish I had the time to show you the different ways I tried this. I tried letting u be 2t plus 1, and maybe there's a way out of that. I tried letting u be sine of 2t plus 1. Then the derivative included, among other things, a cosine of 2t plus 1, so at least I had a cosine, but I didn't have the other cosine. Had troubles there. I tried letting u be cosine. Then the derivative included, among other things, a sine of 2t plus 1, excuse me. So, and I tried. And then I said, boy, I really wasn't getting anywhere fast, so then I tried this. How about, forget about trig for a second, how about a little algebra? Sometimes we have to get, as it turns out, it's going to be trigonometrically creative, sometimes algebraically creative, and sometimes both. So with a little bit of algebra creativity, we can clearly see these are equal. And now, how about sine of something on cosine of the same thing? That is integral tangent 2t plus 1. How about 1 on cosine? 1 on cosine could be written as secant. And you're thinking, well, that's not good to leave cosines. Well, it is when we recognize that we have an avenue to tangent secant. Tangent secant's antiderivative is secant. So I'm going to let u now be 2t plus 1 here rather than up there. Again, there's probably a way out of this, but I liked it this way. So what do I end up with here? Integral tangent u secant u. I'm just going to write it secant u tangent u just because that's how I'm used to seeing it. And then what's du? Du is 2 dt, but I don't want 2 dt. dt gets replaced by 1/2 du. Therefore, bring the 1/2 out in front. The antiderivative of secant tangent is just secant. In this case, secant of u, but u is 2t plus 1 plus the constant coefficient. Wow. Pretty good. Okay. Let's take a look at h. h dx, x on ln x. I could let u be 1 on x. And the derivative of 1 on x, oh, that's tempting. Derivative of ln x is 1 on x. I could let u be ln x. The derivative then would be 1 on x dx. And take a look. Again, I like looking at this. Oops, I don't know why I put f there. I like looking at this as 1 on x ln x dx. Take a look how this exists right here. This guy, my du, is located here and there. All I'm left with is 1 on u. So this is integral 1 on u. That's maybe the worst integral symbol I've ever made, other than when I made it an f right here before. 1 on u du. Du takes the place of that part, and all I need is a 1 on u. Well, integral 1 on u, what gets me to 1 on u? ln u plus c. But u is ln x. ln x plus c. Now, because I introduced a new ln, first off, when this problem started, x is implied to be positive. If x is positive, does that make ln x positive? Well, if this was ln of 0.1, that's the exponent that turns e into 0.1. That's a negative value. Oh, I have to ensure it's positive. Ooh, man, we're going to have to be careful on that. That's going to be kind of a slap to the face when we look at our answers in the back of the book and we forget those absolute values. All right, 2 more here. I think I'm going to have u be x squared plus 1, but I'm going to think about that for a moment. When I take the derivative of that, I get 2x. I normally don't like x's, but look, there's an x here for it to match up with. Let's give it a shot. U is x squared plus 1. Du is 2x dx. What do I like? I like x dx. I'm actually going to write this, of course, as x on x squared plus 1 dx. That's the way I like to see them. Sorry, I'm bleeding in here. What do I like? I like the x. I like the dx. I don't like the 2. So dx, x dx, which I like, can be replaced, may be replaced by 1/2 du. So what do I have? Integral 1 on u. What am I left with? X dx. What is x dx? Times 1/2 du. And I get 1/2 out in front. ln u, what is u? X squared plus 1 plus c. Do I need absolute values around x squared plus 1? It would just be silly. X squared plus 1 is going to be a positive value. Okay, and J, cotangent 3x. We may be looking at a double, triple angle identity rule here. Let's take a look and see if we have some avenue out of this. I may leave this for you guys because I'm running really short on time, but let's say if I let u be 3x, I get cotangent u. What's the derivative that gets me straight to cotangent? The derivative of what gets me straight to cotangent? We don't have one. So what are my options? I could call this cosine on sine, or this could be written as the integral. See, this is tangent. 1 on cotangent is tangent. So this is sine of 3x on cosine 3x dx. Now, u could be 3x. We were in this position a little bit ago, weren't we? U could be 3x. U could be sine of 3x. U could be cosine of 3x. If u is sine of 3x, watch this. If u is sine of 3x, then du is cosine of 3x dx, which is a bad mixture because the cosine's not where it belongs. The dx is where it belongs, like in a numerator. Bad choice. How about u is cosine of 3x, du is negative, oh, you know what, this was times 3 as well. Sorry, 3 times cosine 3x dx. So this is negative, do this again, du is negative, inside derivative 3x times sine of 3x. Dx? What do I like? Sine of 3x dx, they're both on the same level. They're both numerators. I don't like the negative 3, so sine of 3x dx may be replaced by negative 1/3 du. See it? I love that guy. That is this. All that's left is to go 1 on u times negative 1/3 du. So negative 1/3 ln u. U is cosine of 3x. Careful, we're going to come back to that. Plus c. Could cosine of 3x be a negative value? Yes, we don't want it to be. Therefore, absolute value. And there we have it. That is U-substitution. Now, taking this forward, as I said, I'm going to have to go. I'm not going to have time to finish this. I'll come back to it. We're going to be doing the same kind of thing right here. We're going to figure out what we're going to do. I'm probably going to call u tangent of x because the derivative of tangent of x is secant squared. And then I'm going to find my antiderivative. I'm not going to put a c there. I'm just going to end up putting somewhere down the line something from 0 to negative pi on 4. And then I'm going to put 0 into my result and subtract from that, put negative pi on 4 into my result, just like we were finding integrals before we were doing U-substitution. So you are equipped at this point. Thanks for tuning in. Hopefully tomorrow I'll be able to back these guys up with video work on the remaining problems, but I truly believe you are set to go on this assignment. There is our assignment. Might want to pause, take a look at that, and thanks for tuning in.